Welcome back to the second part of section 2. In this part, we're going to be looking at how we can do calculus on these vector functions.
So the first thing we need is a vector valued function. So a vector value function is a vector to describe a curve. And so in this curve, each of these lines is a vector that's going to describe the curve. The curve is described by the terminal point or the head of the vector, the point on at the end of the arrow. And these points just start down here and they just go this way. It actually reminds me a lot of polar coordinates because you have that radius because it's always coming from the center. These are position vectors. So the tail, the initial point, is always at the origin, just like in a polar coordinate system. However, we're not using angles to describe the direction of the point. We're using a vector, which, as opposed to an angle, is basically a slope. So we're using a slope and a radius to describe, or magnitude for vector, to describe where the point is at any given point. And so, so the one point is a single vector, r equals just xy. One point on the curve, it could be the curve, like all of the points, we'd get a function of x and a function of y. So r of t would equal x of t, comma, y of t. And so x is changing and y is changing. How are they changing? They could be changing in a way that makes sense as a combination. They could be changing in a way that does not make much sense as a combination, but that's okay. What's crazy about these vector functions is they can stop, like it can be a finite thing. It could go on forever in either direction. It can curve back on itself in a couple different ways. One way it could curve back on itself is it could, I'll just use this, actually go over here. We could have a vector function that does this weird curve and ends up hitting itself, and then it just keeps rewriting over itself as we go to infinity. So a lot of times in that case, we wouldn't necessarily keep going over and over and over. We'd get one cycle of it and cut it off, kind of like on a unit circle. Yes, we could go around multiple times, but we usually think of 0 to 2 pi. So here, it could just keep going and going, but it could make a closed loop. Another thing it could do, we could start somewhere, and it could go over and then kind of curve back, intersect itself, and go intersect itself, and then just keep going, and then it could go off this direction too if we go the other direction. And it could go both directions, but it could intersect itself several different times along the way. The molecules, where the chemical bonds, they pull it and they make these weird shapes. Not inorganic, but more of the organic molecules like proteins. That's what I'm thinking of, proteins. These vector functions can be used to describe the shapes of proteins, which is hugely important in organic chemical engineering, or some of those crazy topics that you guys are going to be studying and doing amazing things in the future. But the vector functions are very useful in those situations. So as we're looking at these vector functions, there's really two ways we can be looking at them. The first way is as a parametric equation, because we have x of t and y of t. So we have these two equations that are just going in to form a vector. So we can think of it as that. We could also think of it as a vector value function, which means that we have the two dependent variables, x and y, which are the components of our vector r, and each varies with respect to a single independent variable that often represents time. It's very similar to parametric equations. Like there's really not much difference, with the exception that in a parametric equation you have the one point, x of t, y of t. Well, that's going to be the terminal point or the head of the position vector for the r of t, which is x of t, y of t. Is that hugely important as a difference? Not really. These and parametric equations are very, very similar to each other. So we can make lines in a plane. Should have been faded in. So a line in a plane, a line, we use two things to describe a line. We can either use a point or 2 points. We can use 2 points, or we can use a point and a direction. Usually we call the direction a slope, but a vector is a direction, has magnitude and direction. And so the vector is the direction. So here we have a line. We have a whole bunch of stuff going on in this diagram. But we have our initial point right over there. And then we have a terminal point right over there. It's a variable point is what it's calling it. The direction, we have vector v, there is the direction. And so how could we write an equation for this? One way we could write an equation for this is using our vector xy. It's going to equal the initial point plus t times the vector, the direction vector. So we're going to do that with this equation. Actually, it's up. Why not do it with this equation right now? So we have our initial point. So our vector xy is going to equal the initial vector. So we're going to turn the point into a vector, 1, 2, plus t times the direction vector, 5, -3. That's it. That would be the equation of the line here, and t would go from 0 to infinity. Ooh, not or equal to there, just less than. T is not actually going to equal infinity. That would be unfortunate. And in fact, not even 0. I'm gonna erase that. That. It's okay. I just need to change everything. The t was fine. Other than that, how about we go to negative infinity is less than t is less than infinity. So, because it could go in the negative direction, it could go in the positive direction, it could go out as far as it wants. It's just going to be in that direction. We can simplify this equation just a little bit, where r is going to equal r naught. That's the initial r. Notice that's over here. It's the same as that. Plus t times v. We already saw that v was that vector going up. And so that's just a simpler way. Notice the bold. The bold, those are all vectors. The t is not. The t is a scalar. We could take this vector, we could write this in polar coordinates. Or not polar, I'm sorry, parametric coordinates. We could write it in polar coordinates as well, but we're not going to. We could write it in parametric coordinates. Parametric, we're just going to have x equals something and y equals something. Well, x is going to equal the x naught plus t times a. We usually go a times t because ta gets people start giggling. So we go x naught plus at. And then y will equal y naught plus bt. And again, t is going to go from negative infinity to infinity. And so making these parametric equations is really easy. We just take the x component of the vector and the y component of the vector separately, and we can look at those as a parametric equation. What's nice about that, the whole idea of taking things separately, when we get into derivatives and integrals and stuff, we'll be doing the same thing. So this was a line given a point and a vector, a direction. What if we have 2 points? If we have 2 points, we just need to figure out the direction. It's just like finding a slope. We need to find that direction vector. So v, let's go from p naught to p1. It doesn't matter which way we go, just like with a slope, because t could be negative infinity to positive infinity. It'll just switch which way it is. But we'll go from p naught to p1. So how do we get from negative 3 to 4? We add 7. How do we get from 5 to 2? We subtract 3. There's my vector. We have our p naught. We can turn that into a vector to get x comma y. Vector xy will equal negative 3 comma 5 plus t times 7 negative 3. There we go. We could change that into parametric if we wanted to. X equals negative 3 plus 7t. Y equals 5 minus 3t. What if you accidentally used p1 instead of p naught for the initial point? Absolutely nothing. Remember, lines in parametric equations and also lines in vector form, there's not a unique equation. Just like the point slope form of a line in our regular coordinates. If you start out with a different point that's on the line, your equation's going to look different even though it's describing the same line. So the negative 3 plus 7t could easily be 4 plus 7t and 2 minus 3t. Same thing. It just has a different starting point. So, and then what about the equation of a line segment? So here it's not going to go on forever. That's okay. The only difference here is we're going to limit our t. So we're going from negative 1, 3 to 2, negative 1. So let's find our vector. Negative 1 to 2, that's going to be 3. 3 to negative 1 is negative 4. So we have our vector, we have our initial point. So our line segment, x comma y, will equal the initial point, negative 1 comma 3, plus t times our vector, 3, negative 4. And t is going to have a starting point and a stopping point. The starting point, what would give us a value of our p naught? That would be t equals 0. What would give us a value of the ending point? That would be t equals 1. The way we found it, that's going to happen. The only way that wouldn't happen is if you used either a different point along that line, or if you reduced the vector like you would reduce the slope. But if you don't, and in this case, reducing wouldn't make sense. If we had 3 comma negative 6, we could reduce that to 1 comma negative 2. It's the same direction, just different magnitude. In that case, we'd have to worry about our t. But if you just go from one to the other like we did, your t is always going to be from 0 to 1. And we could change this to a parametric equation as well if we wanted to. But I think that at this point, that's probably an easy enough task that you could do that yourself if you care. How about curves? So curves are crazy. We would define a curve as x comma or x of t comma y of t, just like with lines or anything else. It's a vector defined equation, and we could split that up using our unit vectors. X of t times I plus y of t times j, where I is the horizontal component, j is the vertical component. And then x, y are defined on the interval, a to b, where the domain of R is the largest set of values of t on which both x and y are defined. So it just means that the domain is where both of them have to work. So if it doesn't work for x at a certain point, let's say we have x is 1 over t can't equal 0. And if y is the natural log of t has to be greater than 0. So it has to work for both. We can't have a number and then an undefined. That doesn't work. It has to be a number and a number. And so, with curves, we have a curve, same idea. Here we're going from A to B, and we have all sorts of values in between. And again, these curves can do all sorts of crazy things. So examples, like what are some of these things it could do? Describe the curve defined by the function r of t equals a cosine t and then a sine t for t equals 0 to 2 pi and a is greater than 0. If we remember back to our parametric equations, x equals a cosine t, y equals a sine t is going to make a circle starting there and going that way around the circle. Here we'll give it direction there, with a radius of a. And we could plug points in to find that out if we wanted to, but that's just going to give us a circle it's going to give us a unit circle in the way we would follow the unit circle with a radius of a. That's what it's going to give us. And so what about this other one where we have e to the negative t over 10 cosine t, e to the negative t over 10 sine t? Well, that looks like a circle. We've got cosine t and sine t, but the radius is e to the negative t over 10. Remember, that's going to be 1 over e t over 10. That's going to change as t increases. So if we wanted to start out, we'd start out at 0. Well, e to the 0 is 1. So this would be 1 cosine t, 1 sine t. So that's just going to be at the point 1. We'll use the same drawing here. And then as t gets bigger, t over 10 will be a bigger number because we'll have like 1 over 10, 2 over 10, 3 over 10. So that's getting bigger, which makes e to that power a bigger number, which makes 1 over e to that power a smaller number. So as t is getting bigger, as we're going to be going around the circle, the radius is going to be getting smaller. And what does that do? That's going to circle us in and spiral us in to look kind of like that. And so you can find a couple points on the curve if you need to, but just looking at what are we looking at? Where did we start? We started with the circle. Part A is important here, but then the radius was changing, seeing what was happening. Was it getting smaller? Was it getting bigger? Was it oscillating? Well, that's a fun one. When it gets smaller, and then bigger, and then smaller, and then bigger, that's how you start making like clover leaves and stars and stuff. And so that That gets fun. And so, but we can have curves defined by these vector value functions as well. And so now that we have a curve defined, we can talk about limits and continuity. So limits and continuity. Now the fun thing about a limit is that it's one of those things where you can take the x component and the y component completely separately. If we have our function or our vector, let's say the vector r is x of t comma y of t, and the limit as x goes to a of x of t equals L1. The limit as that would be not x, that would be t goes to a. T goes to a of y of t equals some other number, L2. Then the limit as t goes to a of r is going to equal L1 comma L2. So we have the limit. We just find the limit of each of them individually. And then continuity, it's continuous if the limit equals the function at that point. The same thing that it was with functions. If the limit equals what we get when we plug it in, it's continuous. And it has to be from both sides, which you can look at each individual piece, the x component and the y component. If x is continuous and y is continuous, then the vector function will be continuous. So let's look at an example. We have r of t equals 3e to the t over 2, to negative t over 2, and then t over t plus 1. We're going to find the limit as t goes to 2, the limit as t goes to infinity, and then see where r is continuous. So for the limit as t goes to 2, as t is going to 2 in the first one, so we'll have limit as t goes to 2 of 3e to the negative t over 2. That is going to equal, we can plug in 2, we get e to the negative 1 times 3, which will be 3 divided by e. And e is just a number, so it's like 3 divided by 2.7, so this is going to be 1 point something. And then the limit as t goes to 2 of t over t plus 1, that's going to be 2 over 2 plus 1, which will be 2/3. And so the limit as r goes to t is going to equal the vector 3 over e comma 2/3. So it still is a vector because we're going from, it's a position vector. So we're going from the origin to that point, but that's what it is. And the limit is t goes to infinity. So for part B, t goes to infinity. So as t is going to infinity, we have e to the negative infinity times 3. E to the negative infinity, let's write down limit as t goes to infinity of 3e to the negative t over 2. So this is going to be negative infinity, so that'll be e to the negative infinity, which is 1 over e, right? That negative takes us to the bottom. So we have 3 over e to the infinity. That's going to be 3 over an impossibly large number, which is just 0. And then the limit as t goes to infinity of t over t plus 1, that will equal 1. So the limit as t goes to infinity of r of t equals 0, 1. And then part C, we're looking for where is it continuous. So the first piece, the 3, that's not 3, 3e to the negative t over 2, this will be continuous for every value of t because we're not going to have 0 in a denominator, not in the exponent. We can go any number divided by 2. The thing that we'd have to worry about here, that negative exponent makes it 1 over e to the power. So as long as it doesn't equal 0, we're fine, and e to the power will never equal 0. So this is good for all values of t. The second piece, t over t plus 1, doesn't work when t equals negative 1. Right, because that would make the denominator equal to 0. This is not new information. So we just need to combine both of them. We have everything, so there's no restrictions. Here we have a restriction of t can't equal negative 1. So this will be continuous US for all t except t equals negative 1. Or it could be for all t where t doesn't equal negative 1. It could be it's continuous for t not equal to negative 1. I mean, you can say it a whole bunch of ways, but basically t doesn't equal negative 1. If, let's say, the x component wasn't continuous at 2, it would work except for when t equals negative 1 or 2. So we just have to use both. We have to use everything. And so that's limits and continuity. With limits, we can now find derivatives now that we know what a limit is. So the derivative of the vector function is the same as the derivative of a normal function. R prime of t is going to equal the limit as delta t goes to 0 of delta r over delta t. This should look like the limit definition. This will be the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. We can do some calculations. We could plug in the x and y components separately, which really helps out. But what we'll end up getting, r prime of t will equal the vector x prime of t, comma y prime of t. So we just do the derivative to each of these things separately. And it's like magic. That's what I mean by it. It's like almost intuitive. Like you see it, it's like, oh, hey, that's nice. I can do that. I may have even guessed it based on what we saw earlier with splitting these things up. And so the derivative of a tangent, or the derivative and tangent vector, the definition is the same. It's the tangent, that's the tangent vector, it's the velocity. Remember, the end is a position function, so this is the position of a particle, which has direction even. And so the derivative is the velocity in addition to the tangent line. So it has the same meaning as a derivative in the standard function notation that we've been working with all year. So let's find some derivatives. So the first one, r of t equals t cubed, comma, 3t squared, which means the derivative will equal the derivative of t cubed is just 3t squared, and then 3t squared will be 6t. Easy. It's the derivative of a. For b, r prime of t will equal, and this, we could think of this as e to the negative t, comma, 10 root t. It's the same thing. Generally speaking, if it's given in the unit vector, the ij notation, I'd put the answer in that notation, probably because the problem will be easier at some point being in that notation, but also just to get used to it. The derivative of e to the negative t, we're going to have negative e to the negative t times I, plus 10 root t. Well, root t, remember, is t to the 1/2, so that'll be 1/2 t to the negative 1/2, so that'll be 5 t to the negative 1/2, or over root t times j. So those are our two derivatives of that one. With that, we have some derivative rules, and these derivative rules are basically the same as with with our functions. The derivative of a constant is 0. The derivative of a sum is the sum of the derivatives, right? When we have x squared plus x, we can do the derivative of x squared plus the derivative of x. We have the product rule, works the same. The chain rule works the same. So if we have things like a, we have the derivative of u t squared. This is a chain rule issue. So for a, we will get u prime of t squared times the derivative of t squared, which is 2t. So what is u of t? U of t is t comma t squared. So u prime, I'll put it right up here, u prime of t will equal 1 comma 2t. So now we need to substitute t squared in for t. So this will be 1 comma 2t squared times 2t. Notice that the 2t is just a scalar. It's not a vector, and we can multiply that in. And so this will equal 2t, comma, 4t cubed. And then b, we have, let's switch colors here. b, we have t squared times v of t. This is a product rule. So we'll have 2t v of t plus t squared v prime of t. So that'll give us 2t. V of t is going to be sine t, comma 2 cosine t. Plus, I did not judge my space well, t squared times the derivative of that. Derivative of sine is cosine t, comma, derivative of cosine will be negative sine, so negative 2 sine t. And then from here, we can again multiply the pieces in. So we'll have, I'll expand them in a different color so it'll be okay. So we'll have 2t sine t, comma 4t cosine t plus t squared cosine t, comma, negative 2t squared sine t. And then vector addition, we could add these two things together as well. I'm not going to promise it's going to be pretty when we do it, but how nice would it be to have it as a single vector instead of a whole bunch of things? So the derivative of that, the derivative of a product rule could be a single vector, just like the chain rule ended up being a single vector. So we have 2t sine t plus t squared cosine t. Cosine t, comma, 4t cosine t minus 2t squared sine t. And so that would be our vector in just one vector. And so that is the derivative. Those are tangent vectors, tangent lines at any given point along our vector. Some of these, like this last one we did, could make a very interesting graph. I don't know. That could be pretty crazy looking. And so how about integrals? Integrals. Why not do integrals? Actually, before we get there, higher order derivatives. If you want to do the second derivative or the third derivative, you do exactly what you think you would do. Take the derivative of the derivative of that, and you can just keep taking derivatives. It's the exact same. You do them each piece by piece. There's just nothing to it. So integrals of vector value functions, we simply take the integral of each piece separately. So what this says, we take the integral of the first piece, and then we take the integral of the second piece. Then we get plus c. The plus c is a vector. It's not a constant. It is a vector. And it comes from the x components plus c, comma, the y components plus c. Sometimes we can write it as a single c, but it's usually important to note what that c stands for. So let's look at an antiderivative here. We're going to take the antiderivative of each of these separately. So the first one, we get t over square root of t squared plus 2. This is going to be a u substitution type problem. We'll have u equal t squared plus 2. So du equals 2t dt, which means 1/2 du equals t dt. And so that turns this into the antiderivative of 1 over the square root of u, 1/2 du, which u is u to the negative 1/2, so we add 1, we're going to get u to the positive 1/2, divide by our new exponent. So divide by 1/2 is going to be like multiplying by 2. So that gets rid of that 1/2 in the front even. So we have u to the 1/2, which we can substitute back in. U was t squared plus 2. So this will be the root t squared plus 2, comma. So that's the x component. The y component is e to the negative 3t. Well, that's going to be e to the negative 3t divided by negative 3. So negative 1/3 e to the negative 3t. And so that's component. We could change this to the I and j. We have root t squared plus 2i plus or minus 1/3 e to negative 3t j. So that would be the integral of each of them. Don't forget the plus c. That would be plus C1, comma, C2, which could go into the vector, but not usually when it's a constant. And the C1 would come, like here we'd have plus C1, here we'd have plus C2. So there's that. Should have another one. So here, I'm going to have to erase just a little bit. I'll change color. So here, find one antiderivative. So here we get an initial condition. And so we're going to do the same thing. We have the antiderivative of 10 sine t. So we're going to do the antiderivative of 10 is going to be 10t, comma, the antiderivative of sine is going to be negative cosine t plus C1 comma C2, because we have that constant that we have to add, and this is going to be r of t equals this. Then it tells us r of 0 equals 0 comma 1, which means if we plug in 0, we need to get 0 comma 1. So that'll be 10 times 0 comma negative cosine of 0 plus C1 comma C2 0, 1. So 10 times 0 is just 0. And then let's see, cosine of 0 is 1, so this is negative 1 plus C1 comma C2. So 0 plus what equals 0? Well, that's 0 plus 0, so C1 will just be 0. And C2, negative 1 plus what equals 1? That's plus 2. So we have 0 comma 2. That's the constant. Now we could leave it outside, or we could combine it into 1. So we have r of t will equal the 10t plus 0, comma, the negative cosine t plus 2, or 2 minus cosine t. So we can take that plus c and we can move it to the inside piece by piece. It's just vector addition. We add each component separately. So that's integrals. How about definite integrals? Same thing. We just take the definite integral of each piece separately. So we get, yeah, that's it. Take the definite integral of each piece separately. So we want to evaluate this, I plus 3 cosine of t over 2j. So this first one's 1. So we're going to have the antiderivative from 0 to pi of 1 dt times I plus the antiderivative from 0 to pi of 3 cosine t over 2. So I'll put the 3 cosine t over 2 dt times j. So we can move them like that. Antiderivative of 1 is just going to be t. It's just going to be t from 0 to pi times I plus the antiderivative of cosine is going to be sine. So we'll have a sine of x over 2, t over 2. And then if we took the derivative, we'd end up having a times 1/2. So we have to divide by 1/2 or multiply by 2. So that gets us 6 sine of t over 2 from 0 to pi times j. And then we need to plug in our values. We plug in the first one. We have pi minus 0 times I plus, we'll have 6 times, plug it in, sine of pi over 2, that's 1, minus sine of 0 is 0 times j. So pi minus 0, that's just going to be pi I plus 1 minus 0 is 1 times 6 is 6j. So we have pi I plus 6j. So to find the definite integral, we just do it twice. So there's really nothing new as far as the calculus here. It's just we have to do everything twice for one problem. And so that's calculus with vectors. Hopefully it seems logical, at least, and doable, because it's what we've been doing. Most of the time, the derivatives, the integrals, the limits are not going to be the super hard ones that we've done. They're going to be the easier ones. Most of the time, the harder ones could be thrown in there. But just do things to each piece separately, and you should be good to go. So, important is to keep working problems, keep asking questions, and as always, happy mathing.